Okay guys, in this video I'm going to explain use Zener diode. Okay, now this is the basic symbol for Zener diode. So this side it is anode and this side it is cathode. So if you look at the characteristic curve of Zener diode, it is similar to general diode, but we have specific special way of using it. For example, although other diodes we use them as like a valve, so to restrict current direction, but Zener diode we use them as a voltage reference. So we utilize this one around reverse bias area of the characteristic curve. For example, if you look at this one, uh, yeah, so we utilize around this voltage. This voltage we call breakdown voltage. So for example, if we say like 5 volt Zener diode, so the breakdown of voltage of that Zener diode is 5 volts, something like that. And also we have a few important data in this characteristic curve of the Zener diode. So this point we call knee current. In order to use Zener diode as a voltage reference, we need to maintain this minimum current through this Zener diode, IZK Zener knee current. If you look at the data sheets, the information that you can find is the Zener test current, and also then you can find Zener maximum current. When we are using Zener diode, we should not exceed this maximum current point as well. That is also very important data. Okay, and these are two different types of breakdown voltage. So one is like Zener breakdown. So when we use Zener diode like less than 8 volt, so the breakdown is Zener breakdown. So when we reverse bias the Zener diode, what happens is it increases the kinetic energy of electrons, and then they move with high velocity, and also these high velocity electron collide each other and in the atom and also with other atom, and it gives like a rays of the free electron. Then these free electrons give you high conduction, so that is what Zener breakdown is. But second breakdown type, that is avalanche breakdown. So when we apply higher voltage across the diode, so because of this electric field, uh, it increases the electric field through the junction. Then it exerts some force on the electrons at the junction and free them from the covalent bond. So this conduction happened because of these free electrons. Now this breakdown we call avalanche breakdown. Now these are the two characteristic for like two breakdowns. So both are we use in reverse biased region. Now this is avalanche breakdown. So you can see it has a bit of smooth curve compared to Zener breakdown. It happened in low voltage. So this is a bit of rapid change compared to avalanche breakdown. Now we can compare these two type of breakdown. So in this way. For example, like voltage 5 to 8 area, we can expect in a breakdown, and after that it's avalanche breakdown. So with the temperature, when the temperature increase, uh, it decrease the breakdown voltage for Zener breakdown. Increased temperature, increase the breakdown voltage for avalanche breakdown. And both of these breakdown occurred with highly doped semiconductor. Okay, now this is important. This is ideal model of Zener diode. We can represent Zener diode with the voltage source. This VZ, that is the rated voltage of the Zener diode. Ideal characteristic curve, so you can find here. So there's no angle here. It is like straight line. Just after the Zener voltage, it should conduct if you look at the ideal model. But practical model, it is different. So we connect resistor in series, that is the internal resistance of the Zener diode. So you see this angle because of this resistance in the Zener diode. Practical Zener diode, we have this characteristic curve. If you want to find the internal resistance, so by dividing change in the voltage by with the change in the currents, you can easily find this internal resistance. Okay, now, so here, this topic is important. So what will happen with the temperature? What will happen to the voltage of the Zener diode? Now, Zener diodes generally they have like positive temperature coefficient. So we express like percentage. Uh, percentage like this. Percentage. So like per centigrade increase. So what will be the increase in voltage? That is how we express it. Now we call this one temperature coefficient. Now to find this one, we can use this equation. Delta VZ, that is change in the temperature, that is equal rated voltage VZ multiplied by temperature coefficient multiplied by change in the temperature. For example, if you want me to work on example, just think about we have Zener diode rated at like 12 volt and temperature coefficient, so that will be, let's say, 0.001 percent difference. So percentage per Celsius. Now let's say delta B, that is equal this 12 multiplied by, that is the rated voltage temperature coefficient, 0.001 divided by 100 because it is percentage. And let's say after 5 centigrade different, what will be happen? So then 5. This will give you the answer for this one. Delta V, that is equal okay, now this will give you the answer 0.006 volt, or that is equal 0.6 millivolt. Now in that way we can find that. Sometime what you get is like we can express this temperature coefficient in volt per centigrade. So other than like percentage. So in this situation, so TC, like for 1 centigrade increase of the centigrade, what will be the change of voltage? In this situation, we don't need to multiply it by the rated voltage. By just multiplying temperature coefficient by the change in the temperature, we are getting this answer. Okay, I hope this is clear to you. And also, power dissipation is important in Zener diode. Like when you're selecting Zener diode, it should be capable of handling particular required power rating of power of that circuits, for example. So we can calculate by multiplying rated voltage with the Zener current, the current through the Zener diode. So now this should not exceed the rated power in the data sheet. Thank you very much for watching.